Alright guys, in this video we're going to talk about resistance in series versus resistance in parallel. We're going to cover concepts such as RT in series circuits versus RT in parallel circuits. Alright, so first we'll start off with an easy circuit. Start off with the 3 resistor series circuit, and then we'll talk about how that differs from a 3 resistor parallel circuit. Alright, so in a 3 resistor series circuit. Alright, so I'm going to keep everything at 1K. And of course these are all ohms. Alright, so one analogy that I like to use with series resistance is kind of like a stream of water. Alright, and the resistors are like rocks in the water that impede the flow. So essentially, you know, the voltage has a potential, we'll just say 9 volts, okay? And again, you know, we're not covering Ohm's law here. We can get that in another video. But we have 9 volts and we have 3 1 kilo ohm resistors. So 9 volts has a potential of 9 volts. And a current is going to be created as a factor between your potential voltage and your total resistance. So back to the analogy, we're talking about rocks in a stream of water that are going to kind of impede or slow down the flow. It won't stop it entirely, but the bigger the rock or the bigger the resistor, the slower the current will flow. And series resistance is defined as only one path for current to flow from the negative side of the battery. That's going to be this little short leg here. That's how you denote the negative side of the battery, to the positive side of the battery. Now, I teach electron flow. I know there may be some arguments about conventional versus electron. Electron flow teaches or gives examples where the electrons flow from the negative to the positive side of the battery. I teach it this way because this is how electrons actually move. Series is defined in a circuit where there's only one path for current to flow. And this is that one path back to the source. Okay, so in a series circuit, to determine the total resistance for the one current that's going to exist in the circuit, or RT, you simply just add up all of the resistive values. Therefore, RT is going to be 3K. Alright, and that's 3 kilo ohms, but I'm actually running out of space on my tablet, so there should be an omega sign after that K. Alright, so easy. In a series circuit, resistances all add up. Total 3K, and then you can use Ohm's law to figure out the current. Now, one thing I will say is that in a series circuit, the current is going to be the same no matter where you measure it. Alright, we're going to continue with a parallel circuit now. Okay, so I'm going to start out drawing the parallel circuit like this with one resistor. So right now at this point it's a series circuit with a single 1K resistor and a 2 volt source. Alright, now here's the thing. Parallel circuits will exist like this, and you know how I said with a series circuit there is only one path for current to flow. Well, here we've introduced another path for current to flow. So we had this path, and now we have this path. Alright, so when calculating parallel resistance, you can't simply add the resistors, because the truth of the matter is you're not actually adding resistance. You're adding another path for current to flow. Alright, so believe it or not, this actually has the opposite effect of adding resistance. It actually reduces the amount of resistance because you've increased and you've added a second path for current to flow. So if current goes up in your circuit, your resistance, your total resistance must go down. So that's the catch. So I'm going to add one more path, so we'll make it like the other. It's a 3 resistor parallel circuit now, all 1K. And again, I'll need to update my stylus so I can do a little bit better than this cheap one. Alright, so we've added a third path for current to flow, thus further reducing the resistance. And again, like I said, that's the catch, because we're adding resistors, but yet resistance is going down. Why? Because current is increasing. Alright, so to understand this, you need to understand the relationship between conductance and resistance. Conductance is equal to the reciprocal of resistance. All right. So what is actually happening here is as we add a resistor or add a path for current to flow, the conductance goes up. It increases. So each path has a value of conductance, or G. All right. And the reciprocal of that is resistance, because we don't know what the resistance anymore is without knowing how well it conducts now that we've added these additional paths for current. So as we add another path for current to flow, conductance goes up, resistance goes down. Okay, so a big part of understanding how the formula was created is understanding that it was created through measuring conductance, because conductance will increase every time we add a new path for current to run. Because conductance total we can measure through a summation of all the branches. GT equals the conductance of path 1 plus the conductance of path 2 plus the conductance of path 3 in this case, because we have 3 paths for current to run. Okay, well, that's all well and good, but we don't care about conductance. We want to find resistance. So what they do is this: the relationship between conductance and resistance is up here. Conductance equals 1 over R. So here's how the formula is created, and I'm going to get rid of the conductance formula so we can have some extra space. Alright, so knowing that conductance formula, what they create is this. They say GT also equals 1 over R1 plus 1 over R2 plus 1 over R3. Alright, so now we have something that we can kind of work with, except we're not solving for conductance total, we're more interested in the resistance total. So what we're going to do is we're going to sub out GT with resistance total. So we're going to erase GT and plug in RT. Alright, well actually, sorry, 1 over RT, because conductance total equals the reciprocal of RT. But we're going to make another correction because we don't want to solve for the reciprocal of RT, which is also equal to conductance total. We want to solve for simply RT. So we've got to reciprocal the other side of the equation, which puts the other side of the equation underneath 1, and this side simply becomes RT. So we have RT, which equals 1 over the reciprocal of R1 plus the reciprocal of R2 plus the reciprocal of R3. So now we can simply take our resistive values of 1K, 1K, and 1K, plug them into R1, R2, and R3, and you should find that the total resistance is 333.3333333 and a third ohms. Alright, so obviously you can do the math in your calculator. There are current divider formulas that apply. If all your resistors are equal, one shortcut is you can take the value of one of the resistors and divide it by the quantity of resistors, and you'll have your RT. However, I give you the formula because your resistors aren't always going to be the same, so it's best to always understand how to calculate that. Alright, so in summation, the final formula that we're going to get to for parallel resistance is that RT equals the reciprocal of 1 over R1 plus 1 over R2 plus 1 over R3, as you see here at the bottom. The differences between series resistance and parallel resistance, why with parallel resistance the formula looks the way it does, 1 over R1 plus 1 over R2 plus 1 over R3, but there is a reason for that. And again, it's all about understanding that with parallel circuits, you're not adding resistance, you're adding another path for current to flow. Alright guys, if you liked the video, go and click like, subscribe. If you have a question, leave a comment below. And If you have a suggestion for another topic that you want me to cover, again, just leave it in the comment section below, and I will try to get to that as soon as I can. Thanks for watching, and we'll see you next time.